So our next test, correlation and regression. I'm going to show both, even though you really just need regression for this, but I'm going to show both just to illustrate this. Correlation and regression is used when you have two continuous or interval ratio variables and you're looking for a relationship between them. So I'm going to, again, use the 2010 GSS. The library that I first like to use is always just to check the variables themselves. So I'm using the EXPSS library. And the two variables that I want to use for this are education. So I'm going to just check that. So this is highest year of school completed. And the nice thing about education is that it's a count. So it's basically telling us how many years of education. And you can see that when we run the value labels here is it's not showing anything, right? So it's basically, these are the missing values. If you have 0 years of education, that's 0. It runs from 0 all the way to 20. 20 is a graduate degree. The other one that I want to look at is income. So we're going to look at GSS 2018. Income is in constant dollars, right? So it's going to show this. This is 1986 constant dollars. And again, if we run the value label here, it's going to not show us the values because if somebody's making $20,000, they're making $20,000. So we have two, in this case, ratio variables. The 0 is meaningful. Means 0 years of education or $0. I'm going to start with a correlation. There is a correlation function in base R. It's called core test. So if we do that, and the order of the variables doesn't really matter for this. So we're not saying one causes the other because it is correlation is not causation, right? So this is just correlation. So we're just going to put our two variables in. Again, order doesn't matter right now. We'll think about order when we do our regression here in a second. So we're just correlating these two to see, is there a relationship between education and income? This is our test statistic, so it's quite large, and there's our p-value, which is less than 0.05, and that's actually our correlation coefficient. So we'll talk about each of these, but this is telling us that there is a statistically significant relationship between education and income. The correlation, because it's positive, tells us as one goes up, the other goes up. So we have a correlation coefficient, or R, of 0.39, which is actually pretty good. That's a fairly, I think it would be like a medium, not quite strong by Cohen's values, but a medium strength correlation suggesting there's a pretty clear relationship between the two. I tend to prefer regression because it gives us some other useful information, which we'll talk about. So in this case, with regression, we're going to run a slightly different formula here. You have some output. You can call it whatever you want. I tend to go with the two variable values, so education by income, and the code here, this is base R, is linear model. Your dependent variable is going to go first. So we're going to assume that education is actually causing income. So we're going to put real rank as our dependent variable. Use the squiggly line because it is dependent upon education. Okay, so that is going to be our formula for a linear model, basic regression. It's not going to generate output down here. It's going to put the output up here as something that we can then interact with. So we're going to run this, and we can see it up there. And then if we want to see the output, we're going to just put that in here. So summarize it, and now we can see our output. So this is giving us a bunch of useful information up here. This is really the key, and then we'll come down and talk about our R-square as well. So this is our independent variable, education. That's our test statistic right there. That's the p-value. Education is a statistically significant predictor. That's great. If anybody was paying attention, the t-value here and the p-value are actually the exact same ones as they are here. So correlation and regression are very, very similar in how they function. So it does tell us that there is a statistically significant relationship between the two. This is our slope coefficient. That's our y-intercept. And what this means here is that for every additional year of education you have, you can expect to make, on average, $2,650 more per year. Again, that's in constant 1986 dollars. Down here, we have our R-square and adjusted R-square. They're both 15, which means about 15% of the variation in income is due to education alone, which is kind of fun. The last piece that I want to show is, let's say that we do find a statistically significant relationship. We can then use the information we have in the model to estimate how much money somebody would make, depending upon how many years of education they have. So this is basically using the power of regression to estimate values. So let's say that I've got a college degree, which would be 16 years of education. How much money would I expect to make per year? We can plug in the equation. So I'm going to just do this right back in R, because R works as a calculator, minus 16,324.2. That is my y-intercept, so we're going to use that, right? Plus, so this is our basic line formula, y is equal to a plus bx. X, in this case, is 16 multiplied, so that's 16 years of education, multiplied by 2650. That's how much money you would make for every additional year of education. So we're plugging in our slope coefficient, or b, and that is going to tell us how much we would expect to make if we had a college degree. $26,075.80, again, in 1986 constant dollars. So we'd have to modify that by an inflation adjustment. But that's how we would actually calculate that, and that's, again, illustrating the power of regression.